Good morning. Let's talk today on phasor operators and try to differentiate between the phasor operators and the phasors. In general, the phasor and the phasor operators they come in picture once we discuss the AC circuit analysis. In general, what we know is that the sources are of the two types, the DC source and the AC source, and what we are talking here is if we have got the AC source, and AC source can have the loads. Prominently, the passive loads are the resistance, the inductance, and the capacitance. So, we'll be talking about the analysis using phasors for these kind of AC. That is, you have got an alternating current source which is now feeding to the loads, maybe resistance, maybe inductance, or the capacitance. And let's see how does we do the analysis of it. So, in general, let's say if you look for a source, we normally derive the source in a common application from the a socket. For example, see here that we have got a socket over here, and these two are the points where you are going to connect the load, which is over here, and you can measure the voltage across this, and using the ammeter you can find out the current through this. This is a resistive load. This is a tungsten filament lamp, and let's try to see what actually is happening. So if I go and try to see, in fact there are two wires, one is the positive, another is the negative, or that's a phase and that's your neutral. So if I want to measure the voltage across it, what I will get is at time t equal to 0, there are some voltage -5, and subsequently, as time progresses, the voltage also starts from -5 to -2, 0, then 2.55, 7, 8, 9, 10. And then, so see here from negative some value, it has gone to 0, and then it started rising and it has gone to a peak value point. This is 10, and then subsequently it has started decreasing, and you can see there are the cyclicity. At time equal to 0, this was 5 volts, and at time equal to 0.001 again it has reached to 5. Similarly, you can see here 7.07, 7.07, 8.66, 8.66, 9.66. So that is a repeating phenomenon. So what we are doing, in fact, is let's just come back as this is a voltmeter, and I am measuring the voltage across it, which is feeding a load. And the interesting segment is this is going to be very fast. I mean, we are presuming that while we are able to measure the voltages at such a small time intervals. Normally, we do it by the oscilloscope, and then we can still. I mean, nobody can see that, so we normally take a glimpse of it. Right. So storage. So you store one cycle or something, or you store it for some duration, and then measure the values at different instances. For example, let's say if I am able to do the measurement, so I get these voltages. So essentially, I mean, if you try to express this mathematically, actually your voltage and current waveforms are like this. The voltage has started from some value at t equal to 0, there was a -5, and then subsequently it has gone up to the 10, and then it started reducing and it has come back again to 0. So is the current. So let's say, I mean, this is not the current through the load that I have considered. Let's say any current which may be a capacitive or inductive in nature. Right. So what we can see from these graphs are they are We did the measurements and then connected the points to make a graph. And what we can see is this is essentially a sinusoid. So if I express my voltage and currents, let's say if I get some expressions like this, V equals 10 sine omega t minus 30 and I equals some value 8 into sine omega t plus 30, where omega is the angular frequency defined by 2 pi f or 2 pi by the t, where the t is the time period that is from one rising to the next rising or from one peak to the another peak. What is the time interval? That's the periodic waveform. That's normally how we define the time period. So that's the time period. And one upon time is called the frequency. That is so frequently the peaks or the zeros are going to come. So that's how it is. I mean, we are talking about the frequencies, how frequently we are going to get the peaks or we're going to get uh, the zeros, or I mean, any point, the co-phasor points should be repeating. So coming back to um, well, so let's begin our analysis and try to see how we are going to do the analysis of these kind of circuits. So in general, we have got V equals 10 sine omega minus 30, and that's we can represent this equation in the phasor form mathematically. That's only a way. That is, if somebody has written 10 under root 2 minus 30, it amounts to tell that, well, this is equal to this one. So that's a symbolic meaning. So for example, let's say somebody says, um, hello, that means he's trying to draw an attention. So that's a symbol. So similarly, we are creating a symbol for this equation by this. It's nothing beyond those symbols. So following the same way, so we can see the amplitude is divided by root 2, that is we are getting the RMS value. But why we are taking RMS is this is what we measure it. You remember that we have got a voltmeter. This voltmeter is actually measuring the RMS value. So we have taken the peak value divided by root 2, which is RMS value of the voltage, and what we are putting here is the phase by which, so at t equal to 0, if I say it was, the phase was at minus 30. Similarly, at t equal to 0, this was at plus 30. So this is RMS and this. And to come for the graphical representation of the phasors, normally there's a concept that we employ is what we have seen just now is, let's take a voltage waveform and a current waveform. This is true for a resistive circuit, and we have got to represent this, we will be using the phasors. Phasors are a snapshot of a rotating vector. Let's take an example of this. So we presume this vector is rotating in time all the way. And the measurements that we are doing here is actually the projection of this on the imaginary axis, right? So though we have got the voltage V projected on this, so at an instant omega t1, the value over here is Vm sine omega t1, and so is the current is, this will be shown by this arrow. So we have got the amplitude of, there are two things what we are talking is, one is the amplitude and another is at what value or what angle. So the angle is measured from 0 So let's say if I say that my voltage is over here, that means that that's the place we are referring to, and it has got an amplitude at this moment equal to this value. All right. So the VM is the total peak value, and this will be reaching at some certain other place. So we are representing this sinusoidal quantity by a single vector, and we have got an understanding. We presume that it is rotating in this space at a speed omega, and we have got the representation in the mathematical format is the RMS value and the angle. We'll be talking about this. So using the graphical symbols over here, we can plot the relationship between the what you can see here is, for example, here voltage and current, they are co-phasors. So at every moment of time, it has got a different value, but as t progresses, so is the voltage and current in the same phase, they keep changing. So it attains a maximum when the voltage is maximum. It attains to zero, the current is zero when the voltage is zero. Right. So what we represent normally is the phasor value as V phasor. That's your voltage phasor. And by Ohm's law, we know that V equals I into R. What it is implying is this is a sinusoidal quantity. This is also a sinusoidal quantity. And the relationship, they are cophasors. Now, whereas if you go for the any of the elements, for example, inductance or the capacitance, in that case, the voltage is given by the j into omega. Now, this imaginary number j starts coming up, which amounts to tell that, well, by Euler's formula, you remember the Euler's formula, wherein you have got e to the power z theta is equal to cos theta plus j sin theta. So the moment if you multiply it by j, there is a phase, the and if you try to understand the cos and sine, this is the two are actually displaced by an angle 90. So we have got the sorry the voltage for the inductance is given by this, and here we can see that this is V is current phasor multiplied by J, so then J makes a 90-degree phase lag. So we say voltage, the current lags by voltage, or current lags by 90 degree from voltage, whereas if you see the capacitance, I'm sorry, here it's not the current, it should not be voltage. Voltage is equal to minus J XC into I. So the current leads here by 90 degree. In general, I can have a RL circuit or a RC circuit or a RLC circuit, and we know that we define the impedance Z equal to R plus JX. So for a circuit where we have got the combination of resistance, inductance, and capacitance, the reactance is XL and XC is now no more true, but then we go for a third quantity called the impedance, which is the summation of the reactance plus resistance. And this quantity itself becomes a complex number. And this complex number, see here, it was precisely by 90 degree which it was shifting. And so we define the reactances which are purely like XL is omega L, XC is the 1 upon omega C. Whereas when you go for a real circuit, it has got both, all of them together, and that's why this becomes a complex number. So what we see here is the voltage current relationship is V equal to Z into I. This was a phasor, this was a phasor, but this wasn't. Here also I have got this phasor, but XL was not a phasor. So the phasor is equal to a scalar multiplied by a phasor. Now here I am seeing the voltage is equal to this phasor is equal to a product of a quantity which is a complex number here into this. So what does it? Isn't it a phasor? It looks like a phasor, but it's not a phasor, right? It's a phasor operator. Why we are calling it operator is because it operates on the phasors to give you a phasor relationship. Essentially, it's a uh, complex number over here, or it can be a matrix of complex numbers or anything. So in general, if you want to talk about, we'll be calling it a phasor operator. So here we are finally saying is that V is equal to the Z, that's a one phasor equal to a phasor operator with another current phasor. So try to understand the difference between the phasors and the phasor operators. The phasors are the one which are revolving. They are revolving vectors snap at certain point, and that's what we plotted. And it actually amounts to tell that, well, this is something over here. Why we are interested in this is to know the phase difference between the different quantities. So we should be very, very clear about phase and the phase. The phase is something which is revolving. The quantity Z is not a quantity which is revolving, it's just a complex number, and that's why it's not a phasor, it's a phasor operator. Thank you. I hope you might have liked this. Thank you very much.